Hello everyone, and welcome to our presentation of a new privacy-first system designed to provide anonymity by mimicking your IP address. Nowadays, almost all communication over the internet is encrypted, but IP addresses are still visible to eavesdroppers and may leak sensitive information. An adversary might use this information to identify clients, to build profiles, or even censor content. Fortunately, there already exist some solutions for hiding your IP address. Network layer anonymity systems provide strong privacy guarantees, but they face some deployment challenges. Some systems may require extensive modifications to the internet. Others, like Tor and Spine, require the cooperation of multiple autonomous systems along the path. Another class of solutions, like the address hiding protocol, are coarse-grained. While they can conceal the client's IP address, they work at the flow level and are susceptible to traffic analysis attacks. Our goal is to design a system that can provide IP address mixing that is both fine-grained and flexible. The properties we desire are to let clients change their IP address rapidly to provide a sort of anonymity in the crowd. Clients should also be able to change their IP address anytime without breaking their connection. These properties can be useful in a number of scenarios. Let's consider one, censorship circumvention. Now suppose Alice wanted to access a censored website. The censor also blocks the Tor entry node's IP address. So Alice decides to use thwart, which behaves essentially like a proxy to the entry node. Unfortunately for Alice, the censor can still identify that Alice is using Tor based on the first few packets of her communication and blocks packets from her IP address. Now, if Alice were to change her IP address in the middle of communication, she can avoid the censor and access the censored website. But how will she change her IP address? At first glance, this seems difficult, if not impossible. If Alice were using TCP, the current cornerstone of the internet, she would break her ongoing connection and have to reestablish it, defeating the purpose of changing her IP address. But if she were using QUIC, the rising star of the internet, this might be doable. So what is QUIC? QUIC is a communication protocol recently developed by Google. It's still in development, but it's seeing increased adoption. Over half of Chrome traffic to Google servers is already in QUIC. DHCP 3, which will come out in a few years, will use QUIC. QUIC offers a whole host of new features, but the key feature MIMIQ uses is its IP address migration. QUIC allows a client to change his IP address without reestablishing the connection. But this alone is not enough. There are a few other problems we have to address. There's the problem of address collision. How can we ensure that different clients do not use the same IP address at the same time? There's also the problem of routing. How do we send traffic back to a client that now has a different IP address? Before we talk about these challenges, let's first discuss the threat model. In our threat model, we have a number of clients connected to the trusted network. Clients run a MIMIQ agent, which can configure the host's IP address and talk to the network. We also have a passive adversary, which may observe all traffic between the trusted network and the server. The adversary may also control some clients on the trusted network and view all data available to them. We also stipulate that the server may not collude with the adversary. Our privacy goals with this system are to make discovering the identity of the client more difficult and to provide a stronger resilience against traffic analysis attacks. To do this, we provide a property called client unlinkability. Essentially, an adversary should not be able to link packets to a particular client. The key factor in achieving this, once again, is QUIC's handling of encryption and its migration features. So let's talk about these challenges some more. The challenges of address collision and routing. To solve these problems, MIMIQ has three key features. There's a client agent, which runs on the client's machine, and there is the allocation server, which runs on the trusted network. Together, these solve the problem of address collisions. There's also the edge switch, which sits at the edge of the trusted network and connects to the wider internet. This switch solves the problem of routing. So let's talk more about address collisions. One simple solution might be to let clients generate their own IP addresses. But to do this effectively might require cryptographic operations. But this comes with a significant computational overhead. Furthermore, adversaries might be able to predict which IP addresses will be generated if they have access to certain clients. Well, how MIMIQ approaches this problem is to have an agent run on the client's host, which talks to the allocation server and retrieves IP addresses. It can modify the client's IP address and trigger connection migrations. We also have an address allocation server that runs on the trusted network. Most edge networks have address servers, such as DHCP servers. So this is not unusual at all. One important benefit of this setup is that it requires no cryptographic operations. Furthermore, it makes it difficult for the adversary to predict which IP addresses will be used. We also randomly assign a lifetime to IP addresses. A client stops using an IP address at the end of its lifetime, and after a delay, the IP address is recycled and assigned to a different client, or perhaps even the same client. The other challenge we face is the routing challenge. To solve this, we assign a switch identifier to each client-facing switch. Each switch has a unique and fixed SID, which is embedded in the IP addresses assigned to its clients. The allocation server also maintains a routing table of these SIDs in the edge switch. This allows us to drastically reduce the size of the forwarding table on the edge switch. Instead of maintaining a mapping of each client's IP address, the edge switch only needs to keep track of these SIDs. Here's a quick example of our routing system. We have a MIMIQ agent running on the client. In the event of a connection migration, the agent sends an IP request to the allocation server. The allocation server generates a new IP address and embeds the SID into this address. It sends the IP address back to the MIMIQ agent, which changes the client's IP address and triggers connection migration. Meanwhile, the allocation server updates the routing table on the edge switch. When the network receives return traffic, all the edge switch must do is get the SID from the packet and forward the packet to the corresponding switch. The switch then forwards the packet to the correct client. Let's now talk about QUIC's connection migration. QUIC's connection migration process involves sending a relatively small token for path validation, which does have some overhead, but this token is encrypted and looks indistinguishable from data. Furthermore, QUIC provides some measure of unlinkability across connection migrations. Packets have connection IDs, but endpoints are required to use a new connection ID after migration. Furthermore, the negotiation of these connection IDs is encrypted, so an adversary cannot tell which connection ID will be used after migration. QUIC also requires that congestion control be reset in the event of a migration. This is important because an adversary cannot use the congestion control window to track a client across migrations, but this might have an impact on performance. To measure this, we set up an experiment with a single client and a single server. We used no allocation server because we only wanted to test the performance impact of migration. We had multiple runs of the experiment, and in each run, the client sent 1,000 requests to download the index.html file of example.com. The 1,000 requests together added up to about 2.7 megabytes. Across these runs, we changed the number of migrations, as well as the propagation delay in the network. Here's a summary of our results. On the x-axis, you see the number of migrations per 100 packets. And on the y-axis, you see the throughput measured in kbps. Each curve represents a different propagation delay, and each point in the graph represents a throughput for that particular frequency of migration and that particular propagation delay. As you'll notice, the performance penalty becomes less severe as propagation delay increases. For example, for a round-trip time of 50 milliseconds, only 10% penalty for a migration frequency of 4, essentially migrating every 25 packets. We believe that 50 milliseconds is a realistic propagation delay, and migrating every 25 packets should be enough to beat most attacks. We also built a prototype using a DHCP off-the-shelf server for the address allocation. With this prototype, the client was able to successfully communicate with the server and perform migration multiple times without having to reestablish its connection. In other words, it worked. In the future, we hope to implement a prototype that scales to the larger networks. We will also conduct a thorough security analysis and systematically evaluate the effectiveness of MIMIQ against traffic analysis attacks. In conclusion, MIMIQ uses QUIC's connection migration features and some routing mobility to allow clients to rapidly change their IP address while minimizing the performance overhead and deployment barriers. Thank you for listening, and please reach out to us if you have any follow-up questions.